Hello, chemistry students. Today we're going to be talking about redox reactions and oxidation states. But first, we're going to do a demo we like to call blowing up gummy bears. The materials we'll need for this lab include test tubes, a Bunsen burner, a weigh boat, a scupula, tongs, our ring stand, our chemicals, and of course enough gummy bears for the experiment and enough to eat, except make sure to wipe the chemicals off your hands before you eat any gummy bears. In this lab, the chemicals that will be reacting with the gummy bears are potassium chlorate and sodium chlorate. So how exactly are we going to blow the gummy bears up? Well, the first step is to weigh the correct amount of sodium or potassium chlorate using stoichiometry. Chemical equations we'll be using will be shown later, but it's really just simple stoichiometry to get the chlorate sample in excess. The next step is to melt the solid chlorate sample into a liquid. The solid potassium chlorate will decompose into liquid potassium chloride and oxygen gas, and the sodium chlorate will react similarly. From there, the gummy bear should be added to the test tube, and the glucose in the gummy bear will react with the oxygen gas in a combustion reaction, which you'll see in a minute. Here you can see Calvin preparing the demo by turning on the gas in the fume hood and lighting the Bunsen burner. Enjoy the demo!
In this demo, we'll be showing the combustion reaction of glucose. Potassium burns a lilac color, and since this reaction took place with the potassium chlorate, a lilac color is the color emitted. The next demo is identical, except for the fact that we are using sodium chlorate instead of potassium chlorate.
We do not condone the actions taken by Samuel Tannen or his hand, and we are not responsible for any harm that may have come to Samuel Tannen or his hand during this demo. The light emitted in this demo is yellow because sodium burns a yellow color. The gummy bears react because of the glucose in them, so we bought sugar-free gummy bears and expected them not to react. These results were very surprising.
I wanna be happy with what I have. I'm caught up in the madness of the fast life. I'm too focused on the women, drugs, and cash. It's temporary happiness, better than none of dollars. Being heartbroken, better than never loving it all. Not a question, no answer. Why some babies born with cancer? Why people having babies but they can't afford pampers? Why girls taking pictures degrading themselves for likes? Why people still racist in this new day and time? Why we fighting by religion, Muslim, Jewish, or Christian? When half of them live in poverty, million of them children. Why we still treating gangsters they ain't regular, man? 2015, brother, yeah, with the plan. Be the change you wish to see in the world. I gotta say a lot of insecure dudes out here beating their girls. Why the government buy weapons for war?
At this point, we realized there is still gummy bear in the tube, and not all of it has reacted yet.
We thought that the sugar-free gummy bears might not react because they don't actually have glucose, but we were wrong about that. Sugar-free gummy bears actually contain a chemical called maltitol, which is a sugar substitute that's less sweet than pure sugar that has almost an identical formula to sucrose, which is in regular sugar. Maltitol contains a glucose-like syrup that likely reacted similarly to regular glucose, which is why we still see this explosion. Alright, so here's a quick review of redox reactions and oxidation state.
What are redox reactions and oxidation states?
Reactions in which electrons are transferred between reactants and products.
Oxidation states describe the degree of oxidation.
Oxidation states are often the charge an atom would have in an ionic compound.
The oxidation number for an element by itself in its free state is always 0.
Okay, so here we have the reaction for the decomposition of potassium chlorate, which is when we melted the solid in the test tube. So here we have 2KClO3, which is our potassium chlorate, and that decomposes to KCl and oxygen gas. As you can see, all three of these molecules have a neutral charge, so their total oxidation state will be 0. So when calculating the oxidation states of KClO3, we know O, oxygen, is going to take a -2 charge, or a -2 oxidation state because its charge is -2. And K will take a +1 charge because it's a group 1 element, so it takes a +1 charge, which leaves us to solve for KCl's oxidation state. So if we take the total oxidation states for each molecule, we can see that 3 atoms of oxygen at a -2 oxidation state will have a -6 oxidation state. And the K, since there's only one atom, it will be +1. So we have +1 with K and -6 with oxygen. So we know that to sum to a 0 oxidation state, total oxidation state, Cl has to be +5. If we go over to KCl over here, we know that K has to be +1, so Cl must be -1 to get that 0 oxidation state. And then since O2 is a gas in its elemental form, O has to have an oxidation state of 0. So which atoms changed oxidation states? Well, chloride went from a +5 on the left-hand side, and on the right-hand side, it goes to a +1. So the change from +5, -1. So the change from +5 to -1 means that chloride gets reduced, and oxygen goes from -2 to 0, so it gets oxidized.
All right, so this one was the combustion of glucose, which is C6H12O6. So starting with the glucose, we know oxygen is going to be -2. So -2 times 6 is -12. And then hydrogen is almost always +1. So 1 times 12 is 12. So we have a 0 total charge right now. So carbon has to be 0. So then next, the oxygen gas, it's just oxygen gas, so it has to be 0. And then the carbon dioxide, we say O is -2. So -2 times 2 is -4. So the carbon has to be +4. And then for the dihydrogen monoxide, oxygen again is -2, and the hydrogen is +1. So carbon on the reactant side is 0, the oxidation state is, and on the product side, the oxidation state is +4. So that means carbon was oxidized. Hydrogen stays at +1 the whole time. So it was neither oxidized nor reduced. And the oxygen goes from -2 to -2, which means nothing, and 0 to -2, which means the oxygen was reduced.
Here's the overall reaction that happened. As you can see, sucrose reacted with potassium chlorate, but you calculate oxidation states the same way. So the hydrogen obviously is +1 throughout on both sides of the equation. And interestingly enough, the oxygen also has a -2 oxidation state on both sides because the elemental form isn't involved here. The only elements that change are carbon and chlorine. From 0 to +4 for carbon, which gets oxidized, and +5 to -1 for chlorine, which gets reduced.